Today, we're going to do two things. The first thing that we're going to do is I'm going to give you your money's worth. If you are paying tuition analogous to the tuition that you would pay at, say, a big university for the equivalent education, what I'm going to tell you this in the first bit would be worth about a fifth of that money, perhaps more, maybe even a third. And the rest of it would all be just filling in the details. In the last day, we have seen two very big ideas, and we'll talk about another third very big idea that we've seen today. So that's 2 days, 3 incredibly profound ideas. The rest is just details. So, big idea. Take notes. Write this down. You probably won't understand most of the things that I'm going to say in the next few minutes. Write them down. Someday you will, and you'll have deep insight. Okay? This is hundreds of thousands of dollars of education speaking right now. Listen.
So different
Big idea number one. Programs are condensation or compressed versions of strings. Versions of this idea appear in something called Kolmogorov complexity, which you probably will hit later on. Turing machines. What else did I write down? Shannon and or Fisher information. Entropy. And the way we implement streams. And by extension, all scheme programs. In fact, all programs. This is minor compared to these. The idea here is that there's some long data structure that's important and for some reason you want to express it. And the best expression of that is a very small, tight, compressed, encoded version. Kolmogorov complexity measures the inherent difficulty in recording a string, the patterns that it contains, where a string means any arbitrary sequence of symbols, such as the output from a program or the program itself. Turing machines are descriptions of machines, of programs in a nice universal way that depends on the Kolmogorov complexity to understand how efficiently you can do that encoding. Shannon-Fisher information is another way of measuring how much structure there is in a signal, basically the same thing that we're talking about here, how much structure there is in a series of symbols. Entropy is another way of doing exactly the same thing. How much structure is there in the universe? Yep.
Is this also sometimes referred to as algorithmic informational context?
Yes. very strongly dependent upon Kolmogorov complexity. Kolmogorov, an amazing man, the modern age's perhaps best mathematician. If you have a chance to study his works and his theories, do so. Perhaps not the equal to Gauss or Euler, but for the modern age, an amazing, amazing man. Streams are a nice, small way we saw to encode this kind of thing here. In the example that I gave at the beginning of recitation yesterday, we were talking about condensing small system descriptions for long behaviors, as we saw. And then algorithmic information and content and complexity is the application of Kolmogorov complexity to our programs and a way of interpreting our programs. It's okay if you don't understand any of this. Write it down. Hopefully you'll run into it later, and you'll see what I mean. We're talking about unifying very, very broad pieces of mathematics and computer science here under a single idea. That is, programs are a condensed, encoded version of their output. Big idea number 2, locality. Another huge, huge, wide-reaching idea. It appears in architecture, in the guise of memory systems. This is computer architecture, that is the design of computers, caches, and memory systems. Prefetching, pre-computation, oops, and the like. We will see a little bit of this, a tiny little. We saw it yesterday in the table, in the memoization mechanism that we used. That we implemented using tables, where we took advantage of the idea that we were going to repeatedly use the same value. And therefore, we stored it in a table so that we didn't have to go through the computation every time or redo the computation every time we needed that value. We effectively pre-computed the results so that we could use them many times. This also extends into pre-computing the results for a program. If you look at the text of a program, you can often reason about the program itself and say, aha, I know that under these conditions, for example, this bit of the code will never run, therefore we can ignore it. Or I know that this bit of the code, if it is run, means that this other bit of the code will not be run, and things like this. Or you can propagate constraints through. And this falls under the rubric of pre-computation. It's also called specialization. Locality is an incredibly powerful and important idea. This is just within computer science that we find it. But you find it everywhere, everywhere, everywhere. You find it in the way the brain is designed, if you take a look at the systems inside the brain. You find it in the way we design roads. You find it in civil engineering. You find it in built architecture. Just about everything uses the idea of locality. That is, once one thing happens, you can predict very strongly the things that are going to happen around it. It's a very deep idea. 3. Yes, they're all related to the same concept that once you have one observation, you can make predictions on subsequent observations based on that one observation. So, for example, the observation is that you wrote a value to a certain variable, say A. You can predict that with a very high degree of certainty that you will be reading that value. So, for example, if you have multiple kinds of data storage, some of which are faster than others, because you just wrote to a value and therefore it's highly probable that you'll read back from that value, you want to keep it in the fastest data storage. You don't want to let it go out to the slow data storage. So that's what's called temporal locality. Once you make one observation, you know that there's going to be another similar observation shortly afterwards. There's also spatial locality. Once you touch one bit of memory, you are very likely to touch the next bits of memory near it. Spatial locality. You can make similar predictions, say, in traffic flow. Once you make the observation that a car passes through one intersection, you know with high probability that he'll pass through the next intersection, continuing on in the same direction rather than turning. There's some chance that they will turn, but it's much more probable they'll go straight. So that's locality. It's the predictive power of a given observation.
The locality and the first idea you had with information content or complexity of what you call programs as
yes.
Things, what's the relationship between is complexity and information content?
No, they're somewhat orthogonal. They're somewhat different. They're not really related. Although you might think that they would be. And let me think about it through the section, and ask me again at the end of the section, and I'll probably be able to give you a better answer. Okay, so number 3. Not nearly as big an idea as the first two. The scheme interpreter is just a program. This is minor compared to the other two. The other two are a big deal. This is important for this course, and the text argues is actually one of the fundamental results of computer science. I can recast it into that, but as it's written here, it's specific only to this particular program. But it does have deep implications. Why? It's just a program. It's an interpreter. What we've been talking about that we've been relying upon to be effectively magic is just a program. It's code that someone wrote down. Let's turn it the other way around. Code that someone wrote down, we can understand. And that code that someone wrote down was able to create a system that we can use to create other things. That interpreter specified a mechanism for working within a new language. And in essence now, all of the bits and pieces that we've been writing have been on top of that language. And we've been specifying our own little languages. Very small ones sometimes. So for example, when we define a new data abstraction, we are creating a new small language. We have a constructor, selectors, mutators, and those are the essence of the language. That's it. Very small language. But that's the language. And the language allows us to express certain concepts in the realm that defines. It's the same idea. A very small version of the same idea, but the same idea. We are writing layers of abstraction. We are creating small languages. Each are appropriate to the problem that we want to solve. And fundamentally, any program that you write does this. You specify a problem domain. you come up with a mechanism to describe that domain, that is, a language, and you write an interpreter or compiler for that language, which allows you to express the ideas that you want to express. In this case, the idea is a pretty powerful one. Scheme interpreter. That's a very powerful idea. But we just wrote it as a program. Okay. Implication here is abstraction, which comes up close to this level of importance.
Did you also say that that's in some way self-recursive or contains the ideas of even decomposition or something?
Yes, yes. The whole, all of engineering is based on that idea, on the idea that you can take a problem, break it down into its components, and analyze the components individually. And that is fundamentally the idea of abstraction. And then build up the problem back up out of the components. Okay. That now leads us into, that's big stuff. And I hope that by your stunned silence, you have been impressed by the fundamental nature of everything I've been saying so far. And you're thinking of the hundreds of thousands of dollars you just saved.
We would all have been on fellowship, so we're not saving it.
Well, true. Let me put it to a different way. You just heard the condensation of hundreds of thousands of dollars of the government's money. And actually some pretty well, I gotta say, I gotta say some pretty well spent money. I mean, the government got their money's worth, I think.
What are the years of Kolmogorov? When did he do
It's all this century, and I think, although I'm not completely sure, John, do you know? No, John, do you know? I mean, oh, Baruch, do you know?
I was interested in
Okay, yeah. I want to say the biggest results came out in the 30s and 40s, but I'm not 100% sure. I'm not at all 100% sure.
That sounds about right, from what I know.
Yeah.
I think it was, around the 30s and 40s, at least the probability stuff we did.
Right. Yeah. Okay. So this leads now into more mundane things, much less heady. Make sure that I'm getting everything here. Okay. What we saw at the very end of the lecture, where we had this hierarchy of different interpretation mechanisms, I want to go over that again so that we see it one more time and fill in some of the details. And this is what I can't remember who asked the question now. Someone asked a question earlier about exactly how things get into the actual. It was John, into the machine language and that's that stuff. So let me draw that hierarchy again. We have the scheme interpreter, which itself was written in scheme but is compiled. And let me write scheme compiler. On top of this, now we are adding the metacircular evaluator. And on top of that, we're implementing ADU scheme. Or maybe we should make that a colon. So far, we're adding an additional layer here, and we haven't really talked about this at all. But we've now seen, we've sort of peeked under the covers here in the scheme interpreter, and we've seen an implementation briefly, and we'll look a lot more at that on the rest of the session, at the scheme interpreter. The scheme interpreter itself was written in scheme using a scheme compiler. And the compiler generates machine code. Underneath this, then, is machine code. And underneath that is actual hardware.
There's a C compiler in there somewhere also.
I don't think that there's a C compiler involved in this.
How does the scheme compiler compile?
The Scheme compiler is written eventually in Scheme. You bootstrap up. I know that's a little bit weird to think about, but yep.
The same scheme that's used for writing the compiler is the same syntax and.
Yes. Yes.
So in a way, we could use the compiler as well.
You could, yes. In fact, you can run the compiler with the scheme that we get. So the actual hardware down here is the transistors and wires that perform the computations for real. And that's what you'll learn about in 2 terms, in December, I believe. That actual hardware implements a language called machine code. We will see a very brief version of that at the end of this week called Register Transfer Language, RTL. That is also known as assembly language. Some of you have heard of it. This is a way to describe in textual form the instructions that get sent to the hardware. That very verbose language is then used to write a compiler, which allows you to translate between scheme and the machine code. Once you have that translation done, you have then machine code that can be run on the hardware. I hope you can see where I'm going with this.
Wait, does the machine code come into play 2 times? 1 as the language in which the scheme compiler is written, and 2 the language into which the scheme compiler converts scheme code? Or
in a sense, but those are 2 separate paths.
Yeah, that's fine, but they're both machine code? Is that
Yes.
Right? Okay.
I am simplifying things here to make this a little bit clearer. The scheme interpreter, in turn, allows us to write scheme, that is, in this case, the metacircular evaluator, and translate it down to the scheme compiler, which brings it to machine code and down to the hardware. Next level up. The metacircular evaluator now allows us to write ADU scheme expressions, which are interpreted in turn into scheme, which then gets interpreted in turn through the compiler into machine code, which then the hardware actually implements. Now, it turns out, dirty little secret, because we're running on modern processors, that is 686 class machines and so forth, there's an additional level of interpretation here, what's called the microcode. That you will learn a little bit about in 2 terms. Between the machine code, which is, for example, standard 8086 instructions, let me stop and say that again. After probably about 1985 or so, no processors were made that really directly interpreted or directly implemented the machine code. They all have a bit of interpretation. So they have on the processor itself a different machine language and a small interpreter that takes in instructions in the machine code and translates them into what's called microcode. And this is just another level of interpretation. So there's translation from, I hope you're getting this stack now, translation from ADU scheme down into MC_eval. MC_eval is translating into the scheme interpreter. The scheme interpreter is translating to the compiler is translating to machine code is translating now to microcode, microcode gets translated down to actual hardware. Every level of translation involves expanding the amount of code and reducing the efficiency of the system overall, but in exchange for reducing the efficiency, we've accepted the power of being able to go up higher and higher here. It would be impossible to write ADU scheme directly in either hardware or microcode in terms of practical reasons, for practical reasons. You could, if you were so motivated, actually go and build a machine that directly implemented ADU scheme. And in fact, that was one strong avenue of research within the artificial intelligence lab at MIT for a while, to create Lisp machines that directly implemented, interpreted Lisp in hardware. They were reasonably successful. Of course, there are no more Lisp machines that you can find except in museums or people's backyards. But the idea was to collapse this level of interpretation.
How much efficiency is lost or would be gained if we did that?
We will, in fact, look at exactly that issue, how much we lose going from here to here, for example. Turns out it's a lot.
And is it equivalent from?
It's about the same every time you go down. Okay. So if you could really, really use direct microcode or direct machine code, you can have something that's blazingly fast. But it's a practical impossibility to write any large system using the very, very low-level stuff here. You have to use these additional layers to build larger and larger systems. Bro.
Why not use the compiler versus the interpreter for scheme?
Why are we going through the interpreter?
This layer of the scheme interpreter.
This allows us to do things like type expressions individually at the machine and have them evaluate individually. It allows us to manipulate our environment, to examine the objects that we have, to go into a debugger and things like that. That's not possible with the compiler.
If you have a sizable program that is, whole system.
Sure, you can, once it works with the interpreter, you can bypass it and take it to the compiler, absolutely. But you lose all of that functionality that we have currently with the interpreter, yes?
Doesn't an interpreter give you some level of machine independence, of hardware independence? Because a compiler has to be for a specific...
An interpreter also has to be for a specific machine, but oftentimes they're much easier to implement than a compiler is. A scheme interpreter can be written for a small, very, very small computer in 1.5K of object code, which is tiny. I mean, you can write that. It is written, in fact, in machine code. It's very, very tiny. On the handout that you have in front of you is a full-blown scheme interpreter. It's 3 pages of code, and that's it. And it's not a particularly efficiently written one. Yeah.
What's typically implemented in the microcode when you have a microcode? And is it hardware or a mix of hardware and software?
This is software. This is software, and I can't explain to you any better right now without a long, month-long digression what the difference between machine code and microcode is. You will see that in 2 months.
Is microcode implemented on all modern processors?
Yes.
Is that to give you processor independence? Like so that you can write
No.
machine code, you don't have to write your machine
Well,
code
in a
exactly
sense,
for your
in a
processor.
sense, what it means is that, for example, in most modern processors are running 8086 instruction sets, and that, in essence, because that's become a standard, that gives some independence.
So it's the microcode that allows that, right?
And it's the microcode that allows that. In fact, what's really happening is the microcode is allowing us to have much, much better architectures internally in the hardware that will allow us to run a somewhat, relatively speaking, high-level language here compared to the hardware, the language at the hardware level. Is anyone familiar with the transmeta computer? So in theory, they're doing a lot of this translation on the fly. They're translating from here to here, here to here. This translation is done on the fly and can be done flexibly. In most other computers, this is done fixed by circuitry or by a small fixed program.
But in either case, it's software, but it's software that's on the hardware.
Yes.
Versus on the
Yes.
chip.
Yes. Yes.
Now, is that the microcode dependent upon that? There's like reduced information set chips?
Reduced instruction set
Instruction
chips.
set,
Right. So, for example, a reduced instruction set chip will have, and most modern processors, in fact, will have microcodes so that they can implement a complex instruction set, which is what all the 8086 instruction sets are.
But if you
Turns
try a
out
chip
it's-
that actually is complex instruction set,
There are none these
there are
days.
none.
Even though most of the chips out there run complex instruction sets, they in fact are reduced instruction set computers, which is because of this layer of interpretation allows you to do that. The reason that that's done is it's much easier to manufacture, design and manufacture a reduced instruction set computer that's very fast, as opposed to a complex instruction set computer. The classic complex, and we're really digressing at this point, I'm sorry. The classic complex instruction set computer is the VAX 11 series, which has, in one instruction, solve polynomial equation. That's one machine instruction. That's not the sort of thing that you would normally put at the machine level. Oh, sorry, it's evaluate polynomial. Okay. We've seen this sort of thing before. What is this also? Yes, these are all abstraction barriers. And so forth. I'm not going to finish it. So we have abstraction barriers. So far, we've been staying on this side color. Heretofore, before this morning, we were staying very firmly on this side of this abstraction barrier. We are now for the first time, or this morning for the first time, we went below this to see how this works underneath. And the way we did that was in the lingua franca that we have, Scheme. We could have used another language, but as Holly was saying, the easiest thing for us to do at this point is to use the language that we know, which is Scheme, which is what confuses things a little bit. And that's why we actually pop up a level to implement the metacircular evaluator in Scheme. But the Scheme interpreter is, in effect, the same thing. And above the metacircular evaluator, we now implement, or we use the MC-eval to implement a new kind of scheme, ADU scheme, which is in fact just a reduced scheme with tags in front of each of the identifiers to make it clear what's what. Okay. Now, with the rest of the session, let's take a look at some examples. So there are a couple of smaller ideas now that we need to make sure that are well understood. The first is we're taking a look at scheme expressions as if they were lists. And I hope that you're all familiar and comfortable with that idea. We've sort of been mentioning it all along. The incredible number of parentheses that you've been writing have been creating list structures if you ignore the fact that we have an interpretation mechanism for it. If you just consider the text that you're writing down when you write a scheme program, it's a list. It's a very deep, involved, complicated list. But you could, for example, draw the box and pointer diagram for it. It would be tedious, and I wouldn't want to assign that to you, but you could do it. I mean, for any of the real big programs. You could do it easily enough. And we saw, one example. Let's see one additional example. Define A to be B. This is a list of 1, 2, 3, 4 elements. Really? No, 3. What's the list? Help me draw the box and pointer diagram here. Yes. Straightforward. It's just a list. We had a bit of desugaring here to do, where this became a sublist. I oddly enough capitalized the Q. Kind of strange. but it's just a list. Because it's just a list, we can use all of our list manipulation prowess, which we've built up, to examine it, take it apart, to change bits of it, and put it back together, which is all that we're going to do. That's it. And we're going to take advantage of the fact that we have prefix notation. Remember, in all scheme expressions, we have an operator followed by a series of arguments. Always. We've always done this. And this should remind you strongly of something. What does it remind you of? If this is not program, but it's data, what did I just create? A tagged data structure, where this is now a tag, and these are the data. If, what others? Plus, cond, let, so forth. Times. These are just tagged data structures now. They're no longer programs. Well, it's still a program, but we're going to interpret it. And by looking at what the tag is, that will give us instructions on how to interpret the rest of the data. And that's a fundamental idea. We know how to do tag-based dispatch. And that's all the interpreter is going to do. We know that when we see a times, for example, at the head of the list, that means the rest of the list is actually representing something which is the product of all of its elements. It's a new kind of data structure. It's a product of all of its elements, and we know how to actually create it. We know how to interpret that. We know how to handle that. And the way we handle it is to take all the elements, evaluate each of them, form their product, and return that as the result. It's simple and straightforward. And that's why the scheme interpreter that you're holding in front of you spans 3 pages. Using prefix notation like this simplifies the issues surrounding syntax and parsing greatly. If we didn't have prefix notation, if we had infix notation, if, for example, some of our expressions looked like if A, then B, else C, or A equals B plus C, where are the operators? Well, the first one is here, and it has sub-operators here and here. The second one is here, and there's a sub-expression with an additional operator there. You can see how parsing that out and doing dispatch on that is going to be much harder, because you have to test first if you have an if in the first position, and if that doesn't succeed, then you have to look to see if you have an equals in the second position, and if that doesn't succeed, there might be a plus in the second position. Even if you do get an equals in the second position, then you have to check for sub-expressions over here where the operator is distributed. Parsing, in this case, where you have infix notation, becomes a tremendously difficult problem. And by simplifying our language, or unifying our language such that we always have the operator in the first position, we get rid of all of those issues. And we no longer need to have a difficult parser, which you haven't seen anything about. And we can just concentrate on building the interpreter instead, on the real issues of interpretation rather than the issues of parsing, which are separate. Okay. So we'll see a tagged data structure, and every time that we find one, we'll do the appropriate dispatch to evaluate it. The other thing that we have to worry about is that we need an environment to do this execution in. And we've been talking about the environment model, and we need now to create first-class environments. First-class meaning we can manipulate them, we can store them, we can create them, we can pass them as arguments. So we need an environment data structure. And we've seen them before. We saw one earlier today, and we'll see a similar one in a couple minutes. But basically, they're like the association table that we had yesterday in section, where we talked about storing additional values, making bindings between variable names or arbitrary structures and pre-computed values. We're going to use the same mechanism now to store to make our bindings for local variables. Okay, so let's take a look at the code. Page number 1. This stuff is so cool. We have two functions that form the basis of really all of the interpreter. It's right there, one page, there you go. Eval and apply. Okay, I'm lying a little bit because there's some underlying structure that you have to provide that's going to be on page 2 and 3. And I'm lying a little bit more because there's additional primitive mechanisms that aren't represented here. So, for example, we're going to use the underlying plus in scheme and the underlying times in scheme. We could go and write those. They'd be tedious and difficult, but we could write them. We're not going to. We're going to cheat a little bit and use the ones that already exist and assume that that they're just atomic, that we can just use them. So let's take a look at a couple examples and see how they actually run through this code. So suppose we had the following expression. That's the expression, just 1. If you were to type 1 into the scheme interpreter, you would hope to get 1 back, right? Or 3 or 527, whatever the number is. How does that work here? Well, we have a read eval print loop. Read eval print and we're going to start here by typing something into the reader, a 1. It's going to generate the list structure for that expression. Well, the list structure for that expression is sort of the trivial list. It's just the value itself, or the symbol itself. This becomes a little bit difficult to correctly speak about. We're going to create the numeral 1 there. And then we're going to pass that to the evaluator. The evaluator will start with a call to eval, which is on the top of the first page. Eval has two arguments, an expression and an environment. So here's the expression 1, and the environment will be coming in. We'll call it the global environment. And we'll ignore what it is for a minute. I'm looking at the code now. I should write this down. Define eval expression environment. Now, where is this going to? The first thing we have is a cond, which is a big dispatch. If we have a number coming in, that's what we return. Now, wait a minute. Number? How did that 1 get converted into a number? Is it a symbol? Is it a value? Is it a numeral? What's going on? Well, we've cheated a little bit because we're using the reader, which is within scheme, to do the dirty work of converting our input into the list structure. And part of that dirty work is converting the numeral 1 into the value 1. We're not going to talk about parsing, which is doing exactly that. We're going to just use the parser that already exists. It's called the reader. So there's a little bit of magic that's happening for us. So we get the value 1 coming in as our expression. Is it a number? It is, therefore we just return it. And so we get 1 back. The value 1. So that was our first example. How about the expression plus 3, 4? Let me fill in more of this. I have symbol, expression is then lookup. I'm going to abbreviate that. Lookup expression in environment. Return that. Otherwise, EQ car of expression ADU colon quote, and that returns the cadder of the expression. We'll get to that in a second. Otherwise, EQ question mark car expression and quote ADU lambda. We then create the list of procedure object, and I'm going to abbreviate that for now. And finally, oh, sorry, not quite finally, EQ car expression, quote, ADU colon if, and then we will do an eval if, which I won't fill in just yet. Finally now, and this is where we get to some of the meat, we have an apply expression, which I also won't fill in because you have it in front of you. So what happens in this particular case? We did this already. What happens here? We have a list which is the symbol plus, and the numbers 3 and the number 4. Expression is that list. We look first to see if the expression is a number. That fails. Is it a symbol? It fails. Is the car of the expression equal to ADU quote? No, it fails. Is the car of the expression equal to ADU lambda, the symbol ADU lambda? No, it fails. Is it ADU if? No, it fails. Therefore, we call apply. What does apply do? It's down at the bottom. Apply procedure on args. And we first test if we have a primitive procedure. If so, we have a little bit of magic here. Apply primitive procedure to the arguments. A little bit of magic there that we won't go into just yet. Otherwise, we check to see if the procedure object is a procedure object is present in the car of the procedure. If so, we call eval. We'll get to that in a minute. Otherwise, we have an error. So what happens in our second example, plus 3, 4? We've called apply on the car of the expression, which will be this. Oh, this reminds me. This version of the evaluator here has flattened all of the abstraction barriers. In the version that you saw this morning, we had abstractions for every single little bit here. So for example, where we're saying car expression here, that would have been operator from the expression. It wouldn't have been car. Where we have cadder of expression, there's an additional expression for that. There's additional special abstraction for that, and so forth. We've flattened it so that it fits, in essence, on two blackboards. And is very, very concrete, and you can see it immediately. You probably don't want to write a real interpreter this way, because it becomes impossible to maintain. You probably really want to write an interpreter like the one you saw this morning, but they're basically the same thing. Okay. So the car of the procedure object, which is, sorry, where were we? So we're applying eval of car to the environment, and then the list of values on the cdr of the expression. Here's the car of the expression, here's the cdr of the expression. We'll ignore the list of values for a minute. What happens here when we call eval? The procedure is the symbol plus, and then we have a list of values as the arguments. Is plus a primitive procedure? Well, I'll tell you right now it is. This is one of the ways we're letting Scheme do some of the back-end dirty work for us. So we apply the primitive procedure plus to the arguments. So we'll run plus on those arguments. And we'll let the underlying scheme take care of that for us. We could write plus and actually do the addition, but as I said before, it becomes a little bit tedious. We'll do it for other things, though. Once that's done, that value gets returned and goes back to apply, which gets returned back to eval, which goes back to the call initially, to the read eval print loop. Gets printed out to our user. Now, what about the second part, where list of values is written in here? It's eval, apply eval of car of expression environment to list of values. Which I should write that up because it's important. Apply eval car expression in the environment to list of values, cdr expression, and environment, and close. So in fact, I skipped a step here unintentionally, which is that we're applying eval of the car of the expression to effectively eval mapped over the rest of it. If you look at the definition of list of values on the next page, on page 2, you'll see that should look very familiar. It's basically map. Except the mapping function is eval. So let's go through this. We know that when we want to perform an application like this, we need to evaluate the operator. This is, remember, the substitution model. We evaluate this and apply it to eval of args. So first we evaluate the operator, then we evaluate each of the arguments and apply the operator to the arguments. First week stuff. Evaluating the operator is this first call here. Eval car of expression, which will be the operator, in the environment. So in this case, the car of the expression is the symbol plus. We come back in. Is it a number? No. Is it a symbol? Yes. And so we look it up in the environment. And we're going to arrange things so that the symbol plus provides us with the primitive procedure underlying in scheme. That gets returned to here. So we have a procedure here, primitive procedure for plus. It'll be passed in as the first argument to apply. The second argument to apply is going to be eval mapped over the arguments. Remember when I talked about the argument list? We talked about the special form, special syntax for lambda, where you say dot and the rest of the arguments. I talked about that things were actually lists, and we were pointing towards this moment right now, where we talk about evaluating the rest of the arguments as a list and packing them up into a list. if you had a special form with dot in the argument list, you would then unpack it according to that because it is in fact a list. So we evaluate each of these arguments. We saw how to do that up here because they're numbers. They get packed into a list, and so this here becomes a list of the value 3 and the value 4. That gets passed to apply. So here this is going to be the primitive plus and the list of arguments 3, 4, like that. These have been evaluated. We check if it's a primitive procedure. It is. And then we apply that primitive procedure plus to the arguments, compute the value, and return it. So that's how this works.
How does apply primitive procedure work?
We're not going to talk about that. We're not going to talk about how apply primitive procedure works. Any questions so far? This is really important stuff, and I want to make sure I don't want to fail where my teacher did, because I didn't understand this the first time I saw it. I want to make sure that you guys do. So let's go to the next example. Do something slightly more complicated. How about, we'll go wild. Ooh. We're racing now. Plus times 3, 4 times 5, 6. We know how to evaluate this for real, but let's see how the interpreter is going to do it. We have a list. Therefore, the first time through a val, we chug down here to the end, the way we saw before. And we do apply of the eval of the car of the expression, which will be this. Or that'll be 1. Eval of that against a val of the rest, which will be a val of this. That'll be 2. So let's follow this branch first. Eval of plus, this is just repeating what we did before, comes in, the expression is plus. Is it a number? No. Is it a symbol? Yes. We look it up in the environment, and we return the special primitive procedure for plus. That comes back, percolates through, comes back to here. And so we apply the primitive procedure plus on the list of values in the cdr of the expression. The cdr of the expression is now, what is it? Man. And this is new chalk.
Not new anymore. What?
3, 4. We made a special trip last night to go buy this chalk. The arguments here, in this case, is a list of 2 elements, each of which is an expression in its own. So what list of values is going to do is map eval over each one of those 2, pack up the result into a list, and return it. So we expect to see in the end, the result should be times 3, 4 will be 12. Times 5, 6. Help me out.
30.
Thank you. I'll make sure you guys are awake. We expect that to be the result, a list of those values. That list will go in here and be applied to the primitive procedure plus. And as we saw before in this example, it'll get added here. How does this work now? We map eval over each of the elements in this list. This is a 2-list element. You should be able to draw the box and pointer diagram for it. The first element, eval is applied to that first. The second element, eval is applied to that in turn. So applying eval to this, well, we've seen how that works. We look at the expression, it's compound, therefore we come down here, and we call apply on the eval of the car, which is times, the symbol asterisk, on the environment. Eval of asterisk on the environment, is it a number? No. Is it a symbol? Yes. We look it up, and return special primitive procedure multiply. That goes back. Times on the rest of the arguments in this case is a list 3 and 4. We know how that works. We generate, each one of them comes through, pops out here, and get bundled into a list, and get returned as a list 3 and 4. So we call primitive procedure times on list 3 and 4. Using apply, we get primitive times list 3 and 4. Is it a primitive procedure? Yes. We apply it. Magic, magic, magic. 12. 12 percolates back through here as a result of this apply, which generated, was this apply here, and generates our first. Remember, this apply was from inside list of values, which is just mapping eval over the list. Take a look at list of values to make sure you understand that. Yeah.
When we look up the symbol plus, it returns primitive procedure add. If we looked up the symbol ADU plus, would it also return
No.
implementation primitive
No.
procedure?
We haven't defined that. It would give you an error.
Oh, do we have ADU times or do?
Well, we're going to use the underlying mathematical.
Okay, so we didn't redefine.
We haven't redefined. We can. We absolutely can, but we haven't yet. Sharon, did you have a question?
So were the only things that we redefined with ADU colon the quote land of the things actually?
Right now,
eval?
the only thing that we've redefined are those special symbols, those special forms. And I'll talk about those in a minute.
This interpreter evaluates the operands left to right, depth first.
The way I'm working it does.
The way on these 3 pages.
And on the way this is written, it sure does.
Yeah. But the operator and operand can be evaluated in arbitrary order because.
In fact, why do we know? Yes. Why do we know that the operands here are evaluated left to right? A priori. Because we're cuttering down the list where? In list of values. When we're mapping eval over the list of values. And that happens left to right.
And it's depth first rather than breadth first because you didn't do anything to make it breadth
Yes,
first.
right. So we've just generated this 12. Walk me through the other one. The same, we're continuing to map eval within list of values over this list. What happens?
Get all the way through to apply.
We come down here, get to apply. Here, this is going to be times. Here, this is going to be list 5, 6. This goes through back to eval with times as expression. The environment we haven't talked about. It's a symbol, yes. We look up, we get that special primitive, we get the primitive procedure multiply. That comes back. This list of values is going to be 3 and 4. We know how those happen. We get the lists back 3 and 4. And then that goes into apply. And apply finds a primitive procedure, and applies it, and we get the value 30. We've recursed one level down because we had sub-expressions here. We're now going to combine those sub-expressions into a list, popping out of list of val. We've applied eval recursively there. And now where were we? What generated this? Well, it was this application of plus to the rest of the arguments here. So plus applied to 12 and 30, what happens there? Well, we have this eval of plus. We know what happens there. And we have a list of values which came back as 12 and 30. We go to apply the primitive add procedure to the arguments. And so we return, in the end, $42. What do you know? Pretty cool, huh? Now let's try something a little more complicated. Yep.
The way that the magic that is primitive proc works, it doesn't need to know what the environment is at that point because everything's been evaluated.
Everything at that point has been evaluated. What happens if it isn't? I mean, how could it not be? Where is the evaluation happening? It's already happening here. Once apply gets called, the arguments have been completely evaluated. Either that or you're getting an error. or either that or in evaluating you've triggered an error. Okay, let's try the next expression. I'm going to have to erase a little bit here, provide some room. Now we'll really go wild. Sorry. ADU lambda of x times xx. You know what? I'm sorry. I want to really make this distinction stand out. So I'm going to write all of our ADU scheme in orange. I should have been doing this from the beginning. So here's our ADU expression. So this is ADU scheme. So we have ADU lambda of x to be our favorite times xx applied to 3. If this were a regular scheme, you would know what it does, right? What value would we expect back? 9. We have a lambda. Here's the lambda expression applied to a value. So what's different between this and the previous version that we had? Well, now in the operator position, we have a lambda expression. That's what's different about this particular example. The arguments are very simple. There's one argument. We know how to evaluate the numbers. We've done that ad infinitum, ad nauseum at this point. So let's see how this works. This is the operator position. It's a list. So by reflexively, we would go, it's a list, therefore we come down here. No. It's a list, but it has a special car. The expression that's getting evaluated here, let me be completely explicit. Here's the operator. Here are the arguments. The operator is a list, and therefore is an expression. Within that expression, we look in the operator position, and we have ADU colon lambda. That expression, when it comes down through the evaluator, is checked here. Is the expression a number? No. Is the expression a symbol? No. Is the car of the expression equal to the symbol ADU quote? No. Is the car of the expression equal to the symbol ADU lambda? Yes, it is. Everybody see that? We have a list, which is the list ADU colon lambda, then a sublist x, and another sublist times xx. So we've triggered here, because the car of that expression, what's in the operator position, is the symbol ADU colon lambda. Then we create a procedure object. And if you look at your handout, a procedure object is a tagged data structure, where the first value is the symbol, quote, procedure object. And you can imagine what the rest of it is, just without even looking at the handout. How have we written down procedure objects? They have 2 parts. Well, 3 now, with the environment model. What are those parts? The parent environment, the parameters, and the body. That's what's here. In this data structure, the tag is procedure-object. We then have the parameters, the cadre of expression. Let's see if that works. The cadre of the expression, maybe I should write this out. This is a 3-element expression, a 3-element list, where the first element is ADU lambda. The second element is a list of 1 element, which is x. And the third element is a list of 3 elements, first one is times, the second is x, and the third is x. So getting back to here, we're creating a procedure object. The parameters are in the cadder of the expression. Is that right? Here's the expression coming in. The cdr of it is here, and the car of that is here. There's the list of parameters. There's only one parameter, but there's the list. The next is going to be the body, which is the cdr. See if that's right. We take the cdr of the cdr of, the cdr car, which is going to give us this expression here, a list of 3 arguments, which is going to be the body. That's going to be this expression here. Question. Can I, using this mechanism, the way it's written here, can I have more than one expression in the body of a lambda? No. We are making the a priori assumption that there is a single list in the body. Because otherwise, taking the cdr here would not work. Because we would get a list of values in the end instead of a single value.
Couldn't you get the whole thing?
You could get the whole thing. You could get the whole thing, but then you would have to handle it differently. So right now we're not going to. We just take the simple mechanism that we know and love. And then we bundle that up with the environment, and there's our procedure object. That's the list that we return from here. We've checked on lambda. We've dispatched on lambda here. We've created a procedure object, which is just a list, since that's our underlying representation for everything. It's a tagged object, tagged with procedure proc obj, or I actually spell it out here, I think. No, proc obj. And we return that. Where's it getting returned to? Well, we're in the midst of evaluating this expression, and since we were evaluating the operator, we must have been doing that here. So we get back from eval special procedure object representation. Then we evaluate the arguments, which we know how to do. It's a list of arguments. It's a list that's 1 element long. So value 3. So 3 comes back. And we send those 2 things to apply. Applies here. Is proc a primitive procedure? No. Is the car of proc the symbol proc obj? Yes, because it's the special primitive procedure that we built up. Therefore,
compound procedures are lists of 3 elements, proc obj tag, this thing, which is a list of 3 elements, and then the environment. Is that?
It's a list of 4 things. The proc object tag, the parameters, the body, and the environment.
So the tag is the name of the procedure itself.
There's no name here.
Isn't there? Okay.
It's just a procedure object. These are nameless procedure objects.
So you said it was 4 elements.
Yes.
Okay. And they're all those 4 elements are all the same at the top level.
Yes.
How do you go from eval to apply? After you got it.
But it already evaluated that equal car expression.
Right, and that was triggered by a call here to evaluate the operator position of the expression.
Yeah.
So now we're over in apply. We're on this branch here. Equal car proc obj. Yes. Let's write this out. So we call eval on cdr proc, or procedure as it's written in the notes, extend environment cdr proc args and cdr Candidate, yeah. Proc. Close, 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 close. Dot, dot, dot. And then the error. Ooh, what's happening here? What's going on? Let me make sure that I didn't drop anything there because that looks suspicious.
You have to skip the tag. So that's one of the
Yeah, that's right.
errors.
Yep, that's right. When we eval the procedure, we need to do what? We need to evaluate the procedure body in an environment. So eval requires an expression and an environment. The expression is the procedure body here, which is the editor of our procedure object. I haven't drawn our procedure object. Perhaps I should over here. And here we go. So this is what's coming back. I'm just going to call it proc object, even though it actually has no name because there's no binding to it. It's going to be a list of 4 elements. Let me call it something else instead because that's just too confusing. I'll just call it procedure object. The first is the symbol proc obj, which is a tag. The second is the parameters, which is a list, in this case, x. The third is the body, which in this case is the expression times x, x. And the fourth is the environment. Whoops. That looks awfully familiar. Doesn't that look very, very much like this? In fact, what is it? It's this where you've changed from that to a different tag, and tag the environment on here. So what have we done to create a procedure object? We've bundled the procedure with the environment. And the fact that we're using a single underlying representation of lists for everything allows us to reuse this structure. Might be a little bit confusing to do that, but if you walk through the mechanics of actually building it up and building up the new version, you can see it could potentially be completely different because we didn't have to build these up in this order. We could have swapped them at this point. We could have put the environment first. We could have done any sort of number of things to change the representation here because this representation is separate from that one over there. That's the way we write it down. Why would we want to have them the same? Because what?
That we evaluate it now, and that's the format in which we evaluate it.
There's a deeper answer that I'm looking for, but that's getting to it. Yep.
Well, for the same reason that when we were analyzing the environmental model, that the sub-environments were the same as the global environment or other sub-environments, just different in place. I know why.
I believe you. I believe you know why.
Well, I raised my hand because I was so excited because this made more sense to me than the environmental model, even though it's the same thing.
Well, good. I'm glad. The reason that we use the same representation here for the way we write it down and the way it is internally here is because that way when we write it down we know what it looks like straight away. This is a natural representation for it. If you were to change it here, it would be somewhat of an artifice. There's no a priori reason to change it when the original representation is so succinct. Okay, Rob's got it now.
If you nested another lambda inside that procedure, then you're going to have self-same structures nested within each other.
Yes. You're going to have self-same structures. If you had a nested lambda here, it would just be the natural extension of it. It would just appear the right way. So all we've done is we've tagged on this environment and changed the symbol. But that's enough. That's enough to continue on. So where were we? We were here. We're calling eval on this procedure object and an extended environment. Now, since we're really out of time at this point, I'm not going to go through what the extended environment does. We have more time on the subject, so we'll pound on it additionally. And you guys, if you noticed, haven't gotten the problem set on this yet. I want to make sure you understand it first. You're welcome.
And cookies too?
Maybe. We extend the environment before we do the eval. What do we do when we do a procedure application? One last idea and then we'll go. We'll finish this out. What do we do when we do a procedure application in the environment model? This should be automatic. We bind the parameters to the values of the arguments. And then we evaluate the body of that in the newly extended environment.
What is extend?
Hang on a sec.
Sorry.
Getting exactly to that question, what is extended environment? So here's the body of the procedure. We went through figuring that out, this red arrow here, the cadader of our procedure object. There's the body. We're going to evaluate the body in an environment where we have taken the formal arguments, the parameters, and bound them to the actual arguments, which are the values. Where did this come from? Where did this come from? It came from up here, which came from down here. So these are evaluated values. This is a list of evaluated arguments here. This is where the apply was being called from once we had the procedure object and its arguments. So in fact, in this particular case, it is the list of one value, 3. They've been evaluated. We now need to bind the formal arguments, which I'll write again slightly more legibly. We need to bind the formal arguments to the actual arguments, and we do that with an extend environment. What extend environment is going to do is it's going to make multiple calls to table insert, what we saw yesterday, where this is one list of formal parameters, this is another list of actual values, and we want to do an individual pairwise binding. So bind the first formal parameter, which is a symbol, in this case the symbol x, to the first actual value, which is the evaluated value which came from list eval. And then we do that incrementally. We bind the second to the second, and the third to the third, and the fourth to the fourth. Hang on a second. That creates a new environment, a new table, a new set of associations, which we then pass in to eval. Then what happens? We try and evaluate the body of the expression times xx. This is where the magic happens. The magic that's exposed here. We know how to do this sort of thing because we've done a couple examples, like +3, 4. So the times comes through. It's a symbol. We do a lookup. We get special primitive procedure. The x comes through, and then the x comes through. They're symbols. We do lookup in the extended environment. We find that value that was stored because of this binding here. When we extended the environment here, and I'm sorry we don't have time to go through this right now, how that actually works. It's basically the same thing as we saw yesterday. We do the binding. We look up the value x. We get back the value 3, because that's what it was bound to as the formal parameter, as the actual parameter. And then that comes back and allows us to evaluate this expression times xx as times 3, 3. And there you just saw the substitution model in action. Okay, question?
I was trying to figure out why we're calling it extend environment rather than make new environment. So after it makes that table of new bindings, does it append it?
Yes,
to the
exactly.
Earlier environment?
Exactly.
And that's so that it can trace the arrows
Exactly.
back to the earlier binding.
So the environment model happens within extended environment, and we create a stack of what will be called frames. Not stack is the wrong word, because we won't be pushing and popping. We'll be consing them on. We'll be creating a tree of frames, and that will form the chain that you've been creating with the environment diagram, following all those links back. This is where that happens.
When you're no longer inside this loop, you're back where the environment was just
Right.
what you had before without that extra step, so you're not killing things.
And look up here is what follows that chain of associations back until it finds the first instance of the argument that you're looking up, or the symbol you're looking up.
Presumably that's why if you make a mistake in your code and you go through sort of debugger, it says 18,000 bindings made.
Yes, right.
You've made about 4.
Yes. Okay, so substitution model happens in part here. Environment model happens in part here. They're all interleaved. And these are the two main procedures. I'm summing up here so that because we're about to finish. These are the two main procedures that form the bulk of everything that you've been doing. They've supported the bulk of everything you've been doing. They are duals of each other. Eval calls apply, and apply calls eval. When we need to know what the value of, when we have an operator that we're applying to arguments, we use within eval, we use apply. When we need to understand, when we need to compute the value of an expression, specifically the body of a compound expression within apply, we use eval in turn.
The escape is when you get into a primitive procedure, right?
Why does this ever stop? It seems to just be bouncing back and forth. And that's why we started with these very primitive procedures, the very simple expressions before. Here's the escape. This is where we get out. When everything comes down to primitive procedures. Now here's what I want you to think about, and we'll talk about probably tomorrow afternoon. These here are the special forms. And we'll think about why we need them to be there and why we couldn't do something there. Why the differences between, what the difference is between those two. Okay, have a good afternoon.